Hey friends, it's a delight to be introducing you to Lyman Page, one of my oldest and greatest of all colleagues, an inspiration, a mentor, a friend, one of the pioneers behind the cosmology experiment called Toco that was the first to reveal the universe was spatially flat, meaning that any triangle that you could make as big as you want in the entirety of the universe will still have its interior angles add up to 180 degrees, just like a triangle on a flat piece of paper. So he measured the curvature of the universe, finding it to be flat. And that's kind of funny because nowadays many people claim the Earth is flat. Well, the Earth isn't flat, but the universe is flat. And Lyman will tell us a little bit about that on today's episode. He'll also recount some stories from the famous Wilkinson microwave anisotropy probe, which he co-led as one of the chief scientists on that program. And if you go to Wikipedia, the source of all knowledge, and you type in the word science, which means knowledge, you will see a picture that was produced by the Wilkinson microwave anisotropy probe, which was co-developed along with Lyman Page and his team members at Princeton and NASA Goddard Space Flight Center. And he's just such a mercurial, wonderful human being. I love working with him. He's brilliant. I always learn something new from him. And he's a gentleman. And he's still got that boyish charm, even at age 64, as he is now, stronger than ever, working harder than ever to uncover the mysteries of the universe. So today you're going to learn some really fascinating lessons. And I hope that you'll really enjoy it and leave a comment as to what's your favorite story from our conversation. Lyman's a great raconteur. And don't forget to leave a review wherever you're watching this. Leave a thumbs up. Comment. Anything will help us in our battle with the eternal cosmic algorithm. And we've grown so much in this year, and I'm so thankful to everyone out there listening or watching Dr. Brian Keating on YouTube or Into the Impossible podcast. Love you all, and looking forward to many, many great things coming in 2022. Stay tuned. You won't want to miss it.
Any sufficiently advanced technology is indistinguishable from magic.
Open the pod bay doors, Hal.
Welcome, everybody, to a special edition of the Into the Impossible podcast. I am your fearful host, Brian Keating. In this time of pandemic podcasting, it is a great thrill to welcome a friend, a mentor, whether he likes it or not, Professor Lyman Page, who is the James S. McDonnell Distinguished University Professor of Physics at Princeton University in Princeton, New Jersey. He's the author most recently of the Little Book of Cosmology, which is delightful in many, many ways. And we'll get into all the ways that it's influenced me. But I want to start, Lyman, by taking you back 22 years ago this month. This will come out in June, I think. 22 years ago is June of 1999. And in that year, you and your team and your graduate students and postdocs released a paper. And that paper had a very understated title. And the title had to do with a measurement of the angular power spectrum of the cosmic microwave background between multipoles of 100 and 400. What is that paper? What was that paper? What does it mean to cosmology? What did it reveal about the universe that no one ever knew before you and your collaborators and teammates made that measurement?
Oh, yeah. Well, thanks for remembering the paper. Yeah. So it was Amber Miller's paper, and that was sort of the core of her thesis. So this was a measurement. Actually, the paper combined a number of measurements we'd made over the years. And the last one was from the Toco experiment that we did in Chile with the crew there, with Mark Devlin at Penn. And what we were able to do is map out the position and amplitude of the first peak in the microwave background. And we were able to show that we're pretty sure it was from the cosmic microwave background because it had the right spectrum. We had a lot of redundancy built into the measurement. It meshed really well with our earlier measurements where we saw the rise of the peak and sort of went over in this experiment because we'd gone to higher frequencies and smaller beams. We could get over the peak. And what the position of the peak told us is that the geometry of the universe is flat, given reasonable assumptions about the Hubble constant. So we were, it was a little understated, but we wanted to, I think these days, of course, we would have put out such a paper with parameter estimates, but we wanted to just stick really closely to the data and get it out there. And as you know, it's a very competitive time. There are a lot of other groups. The Boomerang guys were gearing up, but we had this great measurement, and we were quite proud of it.
And when you look at that, I remember that being sort of the holy grail of cosmology at that time, at least in an experimental capacity, that everybody wanted to measure it. Everybody wanted to make this measurement of the geometry of the universe. And why not? Because, the last person who had made such substantial contributions to measuring geometry was, Aristophanes and, Aristarchus and Samos, and you guys were doing similar things. And, kind of made me wonder what about cosmology today is really tantamount to that is sort of expected on one hand, that we thought the universe was likely to be consistent with the flat universe from arguments going back to Dickey and others, right. But also that the universe, had some surprises up its sleeve as we would find out around that time as well, dark energy, et cetera. Well, is there anything analogous in our field of experimental cosmology that's sort of a known unknown or maybe an unknown known that inspires us the way that you felt back then as a younger professor, that's sort of tantamount to that or equivalent to that? Is there anything, or are we just in a different phase where now we're just, getting the 8th decimal place of numbers, as Rutherford would say?
Yeah, no, I'd say it's very dynamic and fun and exciting field. I think maybe the thing closest to that is the sum of neutrino masses, because we know it has to be something. We don't know exactly what it is, and we can see a path there. We just have to make better and better measurements. Something that is maybe like that, depending on your theoretical prejudice, are finding primordial B modes, but I think I don't think anyone would be surprised if they didn't exist at measurable levels, just at levels above the foregrounds.
So in the past couple of months, maybe 6 months ago, I had Jayant Narlikar, who used to come to UCSD in this very office where I'm at now. And you've been here a few times, but this office where I'm at now is former home of Jeffrey Burbidge. And Jeff Burbidge, my late great colleague, was the close friend and colleague of Fred Hoyle, who is a character in the field of cosmology, titanic theoretical astrophysicist. And I would say that still to this day, Jayant believes in the steady state or the variance thereof. I would ask you, and he's not an ill-informed person. I mean, he can answer. Right. He did foundational contributions in gravity and also in stellar nucleosynthesis and things like that. What would you say to somebody like that? He's not a flat earther. He's not an anti-vaxxer. He's not a global warming denier. What do you say to somebody, Lyman, as one of the world's foremost preeminent experimentalists? How can you, or can you not, convince somebody of the reality of the origin of the universe, at least in the fact that it was once extremely hot, dense, and it had a Big Bang-like characteristic, if not a singularity, something very, very unlike what we exist in today?
I said, probably approach it on two fronts. Maybe on the really basic front, we know it was hotter in the past just from looking at the SC signature, which is now measured with high significance, just the ratio between frequencies as you go back in redshift. I think that's a measurement, right? And if you have a different model, you have to be able to explain that somewhere. The data fit the idea of a hotter universe in the past brilliantly across multiple experiments. That's important. You need to come up with something special to do that. In terms of things like the spatial structure, there is this, I think it was Neil Turok and maybe Rob Crittenden were pushing this idea that you could create, you could make all the patterns we see in the microwave background from causal processes within the horizon, and that would be fine. And then it was my colleague and friend, Dave Spergel, and I should remember who we did this other work with, right? That point, maybe it was Matthias or something, pointed out that that wouldn't be the case for the temperature polarization cross correlation at large angular scales. Because in order to make that, you really have to have superhorizon fluctuations. Because in anyone's model, opposite sides of the universe can't have talked to each other in any reasonable amount of time. So to get a correlation on huge angular scales takes a very special condition. And so then the chain is that, if there have to be superhorizon fluctuations, our cosmic horizon expands into them, we see them. And so this correlation between polarization and temperature then, of course, we measured it with WMAP. So I'd say those are two pretty difficult observations to explain.
Mm-hmm.
They're both really deep, right? I mean, you really have to push something to explain those, because it's not in one spot in the universe. It's the whole universe is like that in terms of clusters going back. It's not any one group of clusters. It's all clusters that do this.
Mm. And when you look at our friends, across the alley over there at the Institute for Advanced Study or elsewhere, where they spend a lot of time thinking about theories of everything, string theories. I've had on Juan Maldacena and others, and there's kind of this quest for an underlying description that will unify all the laws of nature in one law that, as my guest this past month, Michio Kaku, said, it will be the God equation, an equation that will fit in 1 inch long font, and that will represent all the laws of nature. Is there an analog, an experiment? Is there like a decisive experiment? Is there an experiment that would garner the headlines and sort of the attention of the world the way that our theorist colleagues enjoy attention? Or is experiment of a different character? How do you view experiments in this way of they're essential to validating theories, but we don't seem to get as much attention. And I'm not complaining. I get plenty of attention, maybe too much. Some of my colleagues would argue. But why is it that experiment doesn't get more attention? Or maybe that's an okay thing from your perspective?
Well, I don't know. Maybe we're just not as good talking about it. I think there are. So are there analogs? I don't know. Actually, I'm not sure. Is there a theory of everything? I mean, I'm sure there are advances. I can fully believe my theoretical colleagues will figure out a way to tie in gravity and the standard model of particle physics at some point. It may take a while, but they'll get there. And is that itself a theory of everything? I'm not so sure. It always seems to be another layer. Analog for experiment. I think maybe this is just an experimentalist point of view. When we look, we find things we don't expect. Always. Mm-hmm. There's always something little new, some little toehold that can then take you in a whole new direction. Mm-hmm. And it's it's a long process of chipping away and making really sure you understand your measurements, and then slowly, putting the picture together, getting rid of the chaff, and realizing, no, this is really a new aspect of nature, and then theorists compile on. but there's that element that's always going on, and you can, the rate at which you forget theories that weren't quite right is huge, right? And you can even see this in the just in the more standard things. You can say in the microwave background, right? Although the foundations were laid out a long time ago. there were tons and tons and tons of other theories that just increasingly didn't fit the data.
Mm-hmm.
And if the universe had been different, we would have been forgetting about all the theories that we take for granted now. And, and I think in astro, this happens all the time, right? I mean,
Yeah.
a quasar, right? I mean, where did this come from? In particle physics, it would happen, I mean, these neutrinos weren't dreamed up out of nothing.
Right.
I mean, what happened? That neutrinos had mass was a possibility that they had that the mass eigenstates weren't the flavor eigenstates. I mean, these are discoveries on how nature is, and so it's dynamic. The time scales are just much different, and so I'd say there's, in that sense, it's just we're measuring things better. So there isn't I don't think there is an analog, and I don't think you'd have to be maybe a little myopic. Maybe if you're in your field, there's a magic measurement, but I think in general, no. There's too much nature out there to understand better and more deeply. So.
So, speaking of eminent theoreticians and experiment, quote by Paul Dirac, and he said, "I think there is a moral to the story, namely, that it is more important to have beauty in one's equations than to have them fit experiment. It seems that if one is working from the point of view of getting beauty in one's equations, and if one really has sound insight, one is on a sure line of progress." How do you react to that? That it's more important that sort of the theory be beautiful? Because a lot of my colleagues in theory that aren't string theorists assail string theory as being lost in math, as one book recently put it, or not even wrong, as another book put it. What do you make of this? That some theorists say that by virtue of the beauty, the elegance of it, and as your colleague, well, maybe I don't. Never fully understood how the Institute relates to Princeton, but as Natty Seiberg once said, we string theorists are very arrogant. If we find something beyond string theory, we shall call it string theory. So it seems to me that they focus on this as almost unfalsifiable, but a lot of them are based upon the notion that it's too beautiful to be wrong. What do you say about that? Is experiment not the ultimate arbiter of reality?
Yeah, no, I mean, maybe I take a longer view. I don't know if it's wrong, if it was that, and that point of view just doesn't connect with me. What connects with me is, as an observer of theorists, of course, not a theorist, if it is beautiful and it hangs together, there's something there. And it may not reveal something measurable today. It may just be an element of something that leads to something measurable in 100 years, right? If it's logically consistent and connects with reality in enough ways and other things we know, there's probably something really neat there. And just give us some time, let it grow. I mean, these connections that pop out of these theories are, they're wonderful to see in retrospect. As I just taught StatMac,
Mm-hmm.
and this is, this isn't quite an example of what you're saying about, but I think it's related. So Gibbs had there was the Gibbs paradox, and they're all, the theorists of the time were trying to figure out, they knew that if you divided a volume of stuff in half, that the entropy divided in half, right? But they realized that they had to make that work in the equations. They had to assume the particles were indistinguishable, but they didn't know why, and they came up with all these reasons, right? And then it took, 20 or 30 years later, it took quantum mechanics, right? This abstract development in another field, another subfield of physics to see why that was true. And all of a sudden this made sense.
Mm.
So I sort of view, this is, and then, that was based on math. It was developed quite independently, I think, of all the stuff that Gibbs was working on, right? So I can just see that happening, but it happens on a longer time scale, right? So it's all good and works together, and I can see the excitement, and this idea of not even wrong it just doesn't even compute for me.
Well, sticking with beauty and experiment, and now getting rid of the theory component, what is the most beautiful experiment that you've ever been involved with, or that you're ever encountered? Maybe nothing to do with you, but just an experiment that you feel is particularly beautiful or elegant or moving to you almost on a visceral level.
Well, there's so obvious one for stuff. I'll leave aside stuff I've worked on.
Yeah. Okay. Fine. I'll praise that separately in a second.
Yeah. Right. LIGO is a beautiful experiment. Just purely from an experimental point of view, and just the understanding of the noise limits, the pushing of technology, and of course what it was after.
Mm-hmm.
So that was beautiful. There are other, and I don't think beautiful experiments don't have to always make brilliant discoveries like LIGO, but I think Dickey's principle of equivalence experiment was another beautiful experiment, really pushing technique. I really like what the Edvosh, keeping in that line, what the Edvosh group has done. I could come up with a long list. Some of these atomic physics experiments just blow my mind. I mean, this precise control, these amazing clocks, and now these arrays of manipulating atoms. Really, manipulating arrays of atoms and looking at their interactions and excitations. To me, they're all beautiful, and just things that weren't, maybe gravity and equivalence were in the cards when I was a student, but not these other ones. They've just taken our concept of nature and our interaction with nature just to whole new levels.
And you mentioned Dickey. I wanted to bring him up because he's kind of a unique figure in that he made foundational contributions to our understanding in quantum mechanics and gravity and general relativity, but also in experimental physics. Did you ever interact with him? If so, what was he like? Do you have any recollections of meeting him or knowing him?
Oh yeah, no. So he used to, when I first started here at Princeton, he had the office 2 doors down from where I am now, and of course I met him. I'd say hi. He gave me advice, and I've spent a huge amount of my career on the microwave background, by far the majority of it. But I've always wanted to do something else. So soon after I got here, I had this idea of building an experiment to look at the motion of a really low mass particle suspended in a tiny pendulum to see if there were differences from Gaussian fluctuations. And this was inspired by, I think it was an Ashtekar paper. You get that, an order of Planck mass particle with a couple of fluctuations in the metric. And that just sounded really cool to me. So I sort of sketched out, how to do this experiment. And I went and talked with Dickie, and he said, let me think about this. And then he's called me back a couple of days later. He said, all right, Lyman, here's what's wrong with it. Go measure the microwave background. That sounds good to me. And anyway, that was...
He saved you some time.
Yes. And well, it's just... and Ed and offers a bunch of good insights. Part of it. Here's what's going on.
And of course, you were one of the original co-investigators on the WMAP satellite. It was eventually named after my grand advisor, PhD advisor, David Wilkinson. Talk about David. What was he like as I imagine you guys were very close, and that he cast a long shadow on the career that you've gone on to have so distinguished of a career. What was he like as a mentor, as kind of a avuncular figure to you and to others in the CMB community?
Of course, he was the big daddy in the community. I think he trained many of the people. With Partridge, they built the first, experiment dedicated to going after the anisotropy. What were sort of notable aspects? If you went and looked at our list of astrophysical journals, right? He would, and this is back in the day when everyone just had a wall full of astrophysical journals, right? He'd just write on the spine of each, the articles that he was most interested in, and they were really broad. And he liked looking at new techniques, different ways of measuring things, going after different physics, looking for the first stars. I think as the history of CCDs had an element starting with Dave, except he didn't look at objects with them, right? He got some of the first CCDs to not image galaxies, but to image dark spots in the sky to look for extragalactic background light. He was working when I first got here on a new measurement technique using Rydberg atoms, looking at excitations of Rydberg atoms to try to make a more sensitive microwave background receiver. And so he's always doing some of these things. And, and then even in his last decade, he was working on a SETI project. He spent quite a bit of time on it. And this was this is a project that Horowitz at Harvard started, and they were looking. This was optical SETI, so he took Princeton's telescope, and he and Norm Jurasic and Ed Groth, they made a really fast time constant optical receiver, and they synced it up with one up at Harvard, and they were looking at coincidences just on the idea that if there were extraterrestrial life, right, they wouldn't waste their time with radio signals. They'd be beaming laser beams at us, and they'd be encoding it in fast transitions. So he was really broad and in what he liked, and is focused on measurement. Also, always reassessing, and I find I do that more and more. I don't know if I got it from him. I'm sure I got some of it from him, or whether I was just always like that. But I can tell you, even in the as we're trying to finish the design of WMAP, Dave would, maybe we should turn this channel and make it just a polarimeter. It's like, no, Dave, we've got to do this. Anyway, it's just, just ideas about how to measure things and what's interesting, and always pushing, and I think always reassessing what you're doing. So anyway, and just a fun person. We spent lots of time together and
I really saw
lots of ideas.
only met him a couple times. He used to play tennis with one of my late father's friends, Cy Cochin, in the math department.
Sure.
And he was just, as I say, a avuncular figure. And I think that you have some of that DNA in terms of mentorship. And I've always, been curious. Do you ever study leadership? Do you study, kind of mentorship, or is it something that, kind of preternaturally comes to you, as your boyish good looks come to you? Do you have you're kind of like perpetually, like a 32-year-old? Did you ever study, like business, or did you ever work at becoming a mentor? Or do you think it's just a gift that people have or don't have?
Oh man, it's so. I've never really studied it. I've asked lots of questions about it, just, and I've heard lots about it from being on advisory boards and from certainly for WMAP, just seeing how NASA worked was a real eye opener. I mean, I was in tune with just how that structure worked and how their project management worked and how it didn't work and what you had to guard against and things like that. So it was just a matter of just absorbing it by osmosis. And friends in business and, hear about fan out and what you have to guard against. And then as, chair, it's like being thrown in the deep end, right? And it's sink or swim in your mind. So I don't know. So I haven't studied it, but certainly I am aware of it, how these structures work. It's just something to pay attention to.
So in your National Academy page, it's fairly scant, but it has some interesting information. A piece of it is about one of your hobbies, which is sailing, and again you mentioned that sailing in this is important to you, and also that you spent a year in Antarctica. Are those connected in any way? As not a lot of great things happened to the original sailors that went to Antarctica. Were you concerned at all when you went to Antarctica from a nautical point of view, or did you think everything would work out just fine?
No. So I didn't sail there, right?
I know you didn't. No, sorry.
No. So when I went, that would be, I dreamed about it, but
yeah.
No.
The next question.
There, no, I just I can tell you how that happened, and you can. Maybe I shouldn't, but I will.
No, please go.
No, so I was in college.
Yeah, at Bowdoin.
And I had applied to graduate schools half-heartedly. I think I got into some places, but I just wasn't, my head wasn't there. My girlfriend broke up with me. I saw this ad for research in the Antarctic. Thought, that's what I'm going to do. So I did. And I said, that's a good break. I just didn't know what I wanted to do, and that seemed like a good thing. It was exciting, being in the Antarctic. It was something new, something different. So I applied, and I got in, and I went down there and took care of a cosmic ray station, and at first in McMurdo, and then went to the South Pole. Martin Pomerantz was the head of the program. Went to the South Pole, came back to McMurdo, went to the South Pole again, both times with him. The second time was with, we put in a solar telescope, and then McMurdo, and then out. And then I thought I would go to graduate school then. And I spent enough time with Pomerantz that I got to know him pretty well. And I talked with him, and he sort of questioned how much I wanted to go to graduate school, and I did. But anyway, I ended up not applying to graduate school, and I went and I bought an old sailboat and sailed for the next 2.5 years then I applied to graduate school, and that was it.
Now, that leads me, we're going to go out from Antarctica. Now we're going to go off the planet. Now, I want to ask you a question that sometimes I ask people. It's kind of a gauge of your risk tolerance. But if I sent you, if I said you can be one of the first people to go to Mars, what would be would you ask me any questions, or would you just say, sign me up? Are there any questions you would ask me if I said, Lyman, I got a spot for you on a schooner bound for the red planet?
I just want to check out the radiation levels and understand them to make sure it actually make it there. And at this stage of my life, make it back. A few years, I would, I might not worry about making it back, but yeah.
So that's the kind of adventure you'd be willing to go on, an adventure like that. You wouldn't ask, what's the probability that the craft will make it there? It's the radiation exposure on, like a cosmic ray experimentalist. That's great.
The radiation is considerable. I think that's I mean, I looked at that. I'd be inclined. Mm-hmm. I mean, I think if I were. Maybe my wife will come, but if I were in a time in my life where I really had to be more responsible when the kids were growing up, I wouldn't. So It's not. It's some balance of responsibility and this, and I think and it depends how long the trip was, right? I think I still want to get back and be with my family, but now I don't have so many responsibilities that I just go for it. And definitely, I think if you'd asked me after college, I would have gone.
You would have gone, yeah. And maybe if they try to ask you to be department chair again, we can pull that out. You already did your tour of duty there.
I've done it.
I wonder which is harder, going to Mars. Now I want to move farther out into space, and I want to ask you about other life forms. You hinted at Paul Horowitz and some work maybe that David was interested in. But what do you think about extraterrestrial intelligence? Do you think Fermi's paradox is a valid one, or do you think that we are probably alone?
The universe is a big place. I don't know what you mean by intelligence. Is there sentient life like us? It wouldn't surprise me. Mm-hmm. I mean, I'm an experimentalist. I think looking is important.
Yeah.
I just think that I can't imagine there's not life, in something we call biology. It seems hard to suppress, and there are just too many opportunities, and that we should be looking for it. In terms of at our stage or beyond, it wouldn't surprise me. It's not something that keeps me up at night or anything like that, right? I just I would just bet on it, but not not be worried if we didn't find it.
Uh-huh.
I think in terms of all these, whatever ETs visiting Earth, I like Rosanna Dana's take. Right? Why do they always end up out in the country? Why don't I'm not going to believe it till they touch down, in Harvard Yard or something like that.
Well, actually, I looked it up, and of all the sightings around the world, the majority are in America, but the majority, Lyman, I hate to break it to you, are on the East Coast of America.
Oh, really? Oh, well. We're on the East Coast, though.
With Northeast-ish. But yeah, you're right. There could be some in the South, but let's not be prejudiced here.
Lyman. No, not at
all. So behind you, I think I see a bunch of theses. Is that right? Are those theses?
Yes. Yeah.
So you must be incredibly proud. You've had so many wonderful students go on to great heights. Do you feel like a student, is something that can be, I don't want to say made because that seems artificial, but can, what is the right balance of sort of success as a scientist and experiment? Is it something that can be cultivated, or do you need to be born with it? Is there sort of this nature versus nurture argument? From having mentored so many successful students, we started off the podcast talking about Amber Miller, who's now the dean of all of science at University of Southern California, just up the road from me. You've had so many spectacular students. Do they come in just, there's Princeton, or is it, there's something that you can do to bring out the best in these young individuals that put their trust in you as their mentor?
I really don't know. I would say that they are all different. They really are. And there's some level of helping people, letting people, I'd say more is like it, find what works for them and their path. They're all great. And I think a huge part is, for any graduate student, not mine, when they leave, you want any student to be independent, strong, disagreeing with you, right some of the time, not all the time, but just and you just want that to go, and you don't want to suppress that, and to really like science. I think it's the other thing. I mean, I still, I still love what I do. I'm not jaded about it. So anyway, those are the aspects. So I wouldn't say as a philosophy, I don't have a rubric, and I just think, it's working with people to see, just do science to advance.
Right. Yeah. And it's fun to see and gratifying to see in your book, not only some of the guests that I've had on my show, like Paul Steinhardt, and acknowledgments to him and to David Spergel and Dick Bond, who's been on the show, but also to students and postdocs, Casey Wagner, Kevin Crowley, et cetera, many other people that helped out with this book. Let's talk about the book right now, which is an incredible, I think, feat, because it's, the old line, I think it was by Blaise Pascal, who said, I'm sorry I wrote so much. I would have written less if I had less time. And so it's very challenging to write a brief history of the universe. A brief history of the universe by Stephen Hawking is like 300 pages long. What motivated you to write this book, besides the vast sums of money that Princeton, I'm sure, dropped on your desk?
That's right.
Get you out of retirement. Thank you for sending me the signed copy, by the way. I do treasure it.
No. Well, thank you for your. Thank you very much for your kind words. I was very honored. I won a prize many years ago, the Mark Aronson Award, and I had to, as part of accepting that, they asked me to give a public lecture. And I was deeply honored. This was early in my career. And so I really spent a long time trying to put together a story for how it all worked. And it got a reasonably good reception. And I just kept improving it. And at some point I thought I really should write this up. And first it was just a long monograph, and I called it a monograph for years. And then I just kept working on it, and I'd work on it in the summer vacations mostly. And then finally got the courage to go to the Princeton University Press and say, would you publish this? I shopped around a couple of, earlier version, and there were people were receptive and got some good advice. And anyway, I took it to them, and they said, sure. And, they wanted it to be a little longer, but I pushed back. Being short was, I thought, important for a topic so dense, and so
yes.
It's at least for me, it's one of those things. If you read 10,000 words, doesn't mean you're going to get it better than if you read 1,000 words.
Yeah, no, that's true. And there are even studies about that. You retain 1% of what you read anyway. And I love when politicians talk about, so many millions and billions of dollars. And I'm like, you realize they differ by 3 orders of magnitude.
Yeah,
like,
right.
if you retain 1% of 1,000-page book, it's pretty good as a 10,000-page book. But the book is divided into many sections. It has wonderful illustrations. It's very well written as well, Lyman. I found it so readable. I can imagine, a lay I'm a practicing cosmologist, so I could read it extremely quickly. But even a lay audience can read it in an afternoon. I mean, it really doesn't require the dedication of a textbook. I want to run some crazy ideas by you, and add to some of the craziness. We've already talked about one of the theories, aliens. That's one of the endorsers on the back of the book, Avi Loeb. Another by our friend Mark Devlin, who's a co-spokesperson along with Suzanne Staggs and Adrian Lee of the Simons Observatory. He's at UPenn, is one of your former postdocs. I want to ask, what is the universe expanding into? I have an idea, but I want to first ask you this question that I get asked all the time, Lyman. What is the universe expanding into?
What, for me,
How do you answer?
way I view it,
Yeah,
is, it's a well, first you have to define just what you mean by the universe. If it's the observable universe, it's just our horizon is growing. If you want some bigger version, it's a we don't know, and we can't measure it, and it is so it's beyond what we can have access to. And one of the themes of modern cosmology is that it's really prescribed by what we can measure, right? And there's a real separation between what we can know through measurement, and not just multiple serious measurements, cross checks, consistencies between various aspects of things, and what's speculation.
Mm-hmm.
And I just I love the thought that well beyond our horizon, somehow different symmetries in physics take over, or the universe is just completely different. And those are fun to think about, and maybe thinking about them helps inform what we are now. But I think in terms of being able to explain what we see, that's so far not necessary. Mm-hmm. So in what it's expanding into, I'd say our horizon is just expanding into more of what looks just like us. Right. And there's no measurement you can make that separates that from other possibilities. Even though there are measurements that we have made that could distinguish them, right? Yeah. We can tell if the universe has a different topology to some level.
That's right.
We can tell if it's asymmetric to some level, right? These are all things we can tell by measurement, and as far as we know, and when they don't hold, we could tell if, with some bounds, of course, if it were finite.
Mm-hmm.
And it just doesn't look that way. So anyway, that's the way I think about it. So not a direct answer to your question, but I think it's maybe a different take on your question.
Yeah. I want to say, I never had the chance to be your student, but I envy your students for getting to have you as a professor. But I would say, and I want to get your take on this. So when I think about this, I think about what is the universe expanding into? Well, if you go into, the outside of the atmosphere, and you're going on your way to Mars on your space schooner with your wife and so forth, and then you go outside the space capsule and you have a little, aluminum cube, and it's empty, and you open up that cube, and it's got about a cubic meters worth of volume, and you enclose whatever's in there. You just enclose it with, and you seal up the aluminum cube, and you ask, well, what's in there? Well, there's about 400 CMB photons per every cubic centimeter or so, Lyman. And then there might be a proton in there in that whole cubic meter. And the rest, there might be some dark matter in there, but everything else between the dark matter and between the photons and the protons and the neutrons and the croutons is nothing. And that's what we're expanding into. It's that is the nature of what the vacuum of all of space-time is, at least in my notion. So would you fail me for such an answer on a cosmology exam, Lon?
Well, you forgot about the neutrinos, but of course they're
Well,
not going to stay in your box.
They don't play nicely.
So number density, Brian, you're not doing well.
That's true. I added the croutons. I mean, I'm hungry. It's
number density. It's
That's right. That's right. And that actually brings me to something I wanted to ask you. And you talk a lot about the kind of remaining mysteries. And the book really reminds me a lot of Gamov's book. His writing was he's an expert master communicator, and 1, 2, 3 Infinity and other books that he had on cosmology. If you could get an answer, if you could get a single answer, and then some oracle is going to tell you the answer to any one of the questions that are outstanding that you leave in this book, is kind of the cliffhanger. No spoilers are going to be proffered, but what answer would you most like to know about our universe, or even outside of physics, maybe? Besides, what stock or what lottery number should you play, whatever. But tell me, what about science or cosmology specifically, what most would you be fascinated to learn about if you could magically learn this without any effort other than asking the question?
It wouldn't be about anything in the book, but even just going to cosmology, I am just I'm fascinated by this link between information and black holes and the horizon.
Mm-hmm.
And and just how that all works.
Mm-hmm.
And it just I know that it just anyway. I would. So I don't even know how to formulate the question, right? But it would be just a deeper insight to that connection. And I thought Bekenstein's one of my heroes, and when I teach my StatMech class, I do a little section on that, just in the relation between entropies and black holes, and of course Hawking for what came next. But yeah, that and I know my colleagues at the Institute have way deeper thoughts about this. I would just love to be able to understand them better, but it just seems like there's some huge link there that we're missing, and I'd just love to understand better. There's just a link between information. To be, it's obviously out there, right? There's the whole. It went from bit from Wheeler, which as a student I just thought was, absolutely nuts, to now sometimes consuming me, and now this whole one of the Simons projects, it from qubit. Right? Anyway, I think so. Progress along those lines, I think, would I'd love to be able to sink into and really think about and appreciate more.
Fascinating. Okay, Lyman. Well, we have reached the end of the regularly scheduled portion of this podcast interview, and now we're going to do what I call the thrilling 3, where I ask scripted questions of my guest. And I'm so honored to have Lyman Page of Princeton University, who's been a mentor, towering figure in cosmology, recipient of numerous awards, all deservedly so, and really just one of the greatest benefits to being involved with the Simons Observatory is getting to work with you, Lyman, and we never really had a chance to collaborate otherwise. So I thank Jim Simons for spending a little bit of money so that you and I can work together. I'm sure that's his.
Me too. Jim and Marilyn, thank you.
So now we're going to go kind of philosophical here, and they all involve either the deep future of you specifically, of humanity generally, and then your past, advice to your former self. So here we go. First thing is in the future, when you are no longer with us, you will leave an ethical will, hopefully, which is a summary of teachings and maybe wisdom that you have gleaned from your 120 or more years, hopefully, on Earth. I ask you, outside of your scientific knowledge, which we'll get to maybe in a little bit, but is there anything about wisdom or teaching or code or ethics that you've learned in your life that you live by or would encourage others who are kind of an ideological heir to your knowledge? Is there anything that you would bequeath to people like that?
Yeah. So I mean, they're something, what you do for your family and what you do for students are different things. Let me stick for the student side. I think it's sometimes lost that on students, but I deeply believe there is a physical external reality, and there are deep truths about nature that you can find and convey. And if there are these, aliens, maybe we'll get to meet someday, or that we won't, but in our lifetimes, but who knows, communicate with, they will share those same truths. They will have to share a number of them if they're communicating. Can't be anything different. And that we can find that truth and through many avenues. But I think that you can know real things about the world is important to keep in mind. It's not relative. It's not a matter of opinion. It's not, you have a different view. There are things we can truly, deeply know.
Very nice. Okay, now I'm going to go a little bit further into the future, 1 billion years. And this is evocative of Richard Feynman, who said, if in some cataclysm all scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I won't say what he said because I don't want that to influence your statement.
Right.
I know what I would say, and it's actually based on something you did. But at first I want to hear what you would say.
I'm not sure I'd give a sentence. I'd give an image. And I would give the image of the background anisotropy for a bunch of reasons. Well, maybe not a bunch, but a few. One, it's not going to change much in the next billion years. It would, for anyone who is nearby us, it will be the same. And it will be a connection. If we're obliterated, it will be a connection to what we know about of course, the universe, but also all the technologies that went into measuring it and explaining it.
I was going to say the same thing, except I was going to put the angular power spectrum that you measured, the WMAP, because it actually subsumes Feynman's answer. So Feynman's answer was the atomic hypothesis. And the atomic hypothesis, I'll just say it for my listeners who don't know, that little all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they're a little distance apart, repelling upon being squeezed. In that one sentence, you'll see there's an enormous amount of information about the world if just a little imagination is applied. Now, I want to say that the CMB power spectrum that you measured, one of the most iconic images of all time in science, breakthrough of the millennium in many people's estimations, is one that encodes and is necessarily dependent upon the atomic hypothesis, because what makes up the matter It is obviously atoms, and what makes up more of that image is neutrinos and photons and all the other things that go into the universe, and unknown things like dark energy. So it would encapsulate what we know and what we don't know. And I think it's just much more rich than Feynman. So take that, Feynman, wherever you are.
I could also add, if you had a map, you could get the power spectrum.
That's true. But then, me, Lyman, I'm not known for releasing my maps. You know about me and maps, Lyman. Please, let's not get okay. That's personal. Okay, last question, Lyman, and then we're done, and you have a richly deserved weekend ahead of you. Now we're going to go backwards in time. We went forwards in time, 120 years, a billion years. And now we're going to go backwards in time to when you were 22, 23, whatever you were back many years ago. And this harkens to Arthur C. Clarke's 3 laws. The first law is that any sufficiently advanced technology is indistinguishable from magic. And actually, I opened the podcast, you'll hear with his actual voice saying those words. His second law was that for every expert, there's an equal and opposite expert. I like to drop that on my faculty colleagues every now and then. And then the third law is the only way of determining the limits of what's possible is to venture beyond those limits into the impossible. And that's the name of this podcast, Into the Impossible. I'm going to ask you for advice to your former self. What thing did you think was impossible at age 20 or 30, but you would advise yourself on how to do it now that you've had the courage to go into the impossible?
What thing did I think was impossible? Maybe that I'd be president or something. I think in terms of, I would. Yeah. What's the way to? I think it's almost again like I don't think like that. I think I've always tried to do things that were well beyond what I can imagine doing. And usually not knowing it at the time, knowing it in retrospect. But, dreaming big, taking risks. So, I completely agree with him that, discovering the limits of what's possible means going beyond. And I don't know, maybe it should just I can't imagine just not pushing, not trying to go beyond, and not questioning, and not and maybe just as important is being excited about exploring, no matter what it is.
Awesome.
And so, whether your mind or nature or just trying to understand better what's going on. So.
Wonderful. Well, Lyman Page, I want to thank you for being not only a mentor and a friend, but a teacher to many thousands of people around the world, a true explorer of the world and of the universe, and really just an all-around incredible soul. I want to wish you a happy weekend and best of luck with this wonderful book, your second book after Finding the Big Bang, which is behind you on your shelf, and I have a copy that you signed for me a couple of years ago, written with Bruce Partridge and your colleague Jim Peoples. Lyman, have a wonderful day. I'm going to run to my group meeting. I'm going to try to channel some of your infectious good cheer and leadership. Lyman, have a wonderful weekend. Thank you so much for joining us in The Impossible.
Any sufficiently advanced technology is indistinguishable from magic.